So we're getting into the second part of the course, which means we're going to switch gears a little bit. Now the first part of the course dealt with geometry and vectors. You know, we're talking about space. Now we're going to switch and we're going to talk about multivariable functions. So we've talked about parametric curves, which are multivariable in the sense that it lived in 3 dimensions. But it's a curve, so somehow it's like a one-dimensional object living in a 3-dimensional space. So we're going to get up to something that's a little bit more interesting. So we need to remind ourselves what are functions. So a function is, it's like a rule. I like to visualize it as a machine. And so what happens is you have this machinery, you have an input that goes into it, it does something to your input, and out comes an answer. So that's what a function does. Takes input and produces output. Now the only thing that has to be true to be called a function is it has to be consistent. Which is to say, if I put the same thing back in again, I get the same answer back out. All right. So that's a function. Now usually when we think of functions, we think of functions where the inputs are numbers and the outputs are numbers. Which is okay, because that's most of the functions we've seen in our lives, but it's not the only type of functions that we have to look at. For instance, there's a very important function that people care about, where the input are the students, and the output is the grade, and of course this is the curve. It's the most thought about function when it comes to the end of the semester. People are thinking, how does this function work? Tell me more about this wonderful function. Okay, well, we're going to get up into multivariable functions, which means that we're going to start talking about functions where we have multiple inputs. So y equals f of x, that's the type of function that we've been working with up to now, most of the time. We have a single input, we get a number as an output. And for the time being, especially for this part of the course, we're always going to think of our output as being a number. When we get into the third part of our course, we'll start talking about output as vectors, but that's far down the road. So today we're going to get mostly into the second one, which is z as a function of x and y. So now I have 2 variables that affect my output. And what's the next step? Well, 3 variables. So x, y, and z. And then my output, well, of course, we go up the alphabet, x, y, z, and the next letter is w. I don't know why, but that's sort of the convention. Very rarely will we talk about 3-variable functions directly. We will see that there's a nice way to think about 3-variable functions, which helps us solve some small cases. So we will touch on them, but for the most part, we're going to focus on a function with 2 inputs. So z is a function of x and y. So let's do an example. Our function is x squared plus 2y squared, and we want to find the following. Okay, so what does this mean? Well, it says I'm going to give it 2 things. Something in the first slot, which I'm going to refer to that as x, something in the second slot, which I will refer to as y. And what I do is I say, well, whatever comes into the first slot, you square it. Whatever comes into the second slot, you square that and double, and then you add those answers together. So the x squared plus 2y squared, that's our machinery. That's our rule for how we make something new. Okay, so let's try a few of these. F of 0, 2. What are we going to get?
0.
Well, 0 plus 8. So we can even write down 0 plus 8, or we could just simply say it's 8. Okay, that's not so bad. Well, let's try another one. 1, 1. 3, all right? Because you get 1 squared plus 2 times 1 squared. 3. Okay, t, 1. T squared plus 2. So yeah, notice that now these aren't just numbers, this is a symbol. Am I allowed to plug in a symbol? Absolutely. I can put in anything I want. I just have to follow the rule. So the x slot is t, So I'm going to square that, and then I'm going to add 2 times 1 squared. So t squared plus 2. What if I did t plus 1 comma t? Yeah, so the x slot is t plus 1, the y slot is t, so this will become t plus 1 squared plus 2t squared. All right, you ready to think? Here we go. What's f of y comma x? Y squared plus 2x squared. Yes? Because we think of the rule. The rule says these x's and y's here are actually just sort of stand-ins. X generally says it refers to an unknown thing. Similarly for y. So I have 2 unknown things. I just have unknown thing 1, unknown thing 2. But we call them x and y. And so we say, look, it's got to be whatever comes in the first slot, you square it. What comes in the second slot, square double. So here, we've changed the order, but we have to follow the rule. So now the y is in the first slot, so we square it. X is in the second slot, we square it and double. All right. Now, one more. F of cat and dog. What is it? Yeah, cat squared plus 2 dog squared. Now, you might be thinking, I don't know if that makes sense. We don't care. We're going to follow the formula. We have our machinery, we have our rule, we do what the rule tells us. Now, if it doesn't make sense, then that's fine. But oftentimes, that's okay. It does work. You disagree with the cat squared plus 2 dogs squared? Okay, all right. Dogs aren't squared, I understand. Dogs are wonderful creatures, unlike those cats. Okay. The range. The range of a function are all possible outputs. Range is hard. Range is extremely hard because it's not so clear how to find that. And there's a note here that says you need calculus sometime to find extreme values. Now you might say, oh, range can't be that hard. So you might say, look at this function, and I'll ask you, what's the range? What can you get out? Well, certainly we can get 0 out because I can plug in x and y both being 0. And can I get anything that's bigger than 0 out? Can I get anything less than 0? No. So the range here is greater than or equal to 0. Now, this assumes there's no restriction on what we plug in. So in other words, I can plug in any pair of numbers I want, but we'll assume we're going to stay real for a second. But you could imagine that I say, well, look, not only do I have this function, but I have to take the function where I take values over some little region. So maybe there's some rectangle here. And then I say, okay, what if I limit it so that the only numbers you can plug in are these rectangles, points inside this rectangle? Well, what happens? And the answer is, it gets a lot harder. It's not so clear. It's not so clear. Now, because I happen to have the corner at the origin, you can say, well, it's something greater than or equal to 0, but where does it top out? Well, sounds like a good question for us to answer. And by the time we hit our end of this part of the course, before the next exam, we will be able to answer questions like this. But to do that, we have to be able to say, where's the largest thing that can come out? So we are building up to things like that. All right, so range deals with the output. So in other words, the range is what comes out of the machine. The other thing is the input. Well, what do we call the input? The domain. Yes. Now, whereas range is hard, domain tends to be pretty easy because domain, there's more or less only a few things that can happen that cause us headaches. Things we want to avoid. Okay, so let's talk about some common problems. More or less, there's 3 of them. Does anybody know one thing that we should always avoid when we're writing an equation down? Yeah, never divide by 0. So if there's any point in my domain where the denominator is 0, that's it. It's not going to work. So it can't be in my domain. Anything else? Square root of a negative. Good. Even going in the right order. Thank you. Okay. So we can't take square roots of negative numbers in this class. Now, if you want to take a square root of a negative number, you can take a certain class that talks about those things, but it's not calculus. Well, it is calculus, but it's not our kind of calculus. We're saying everything's being nice and real. Real numbers can't come out as square roots of negative numbers. Okay, so those were sort of the two easy ones. Here's one more. Okay, logs. So log of anything that's negative or 0. You can't take log of 0. If you look at the log function, it has a very particular shape in that as you head towards 0, so if this is the graph of log x, you'll see what happens is it's heading off to minus infinity as you head towards 0. So you cannot take log of 0. You might say, well, can I think of it as negative infinity? You shouldn't, but some people might. But the important thing is that it's sort of blowing down. I don't want to say blowing up because it's not going to positive infinity. It's going down. All right. So if we want to find the domain, basically the thing is avoid the problems. So if we can avoid the problems, life is good. So we're going to find and sketch the domain of a function. So here's our function. F of xy is the square root of y minus x squared divided by x squared plus, in parentheses, and parentheses are important. Make sure you pay attention to parentheses, y minus 1 squared. Okay, so we need to avoid problems. The problems will tell us restrictions. What are some things we should be careful of? We should be careful of dividing by 0. All right, so let's look in the denominator and ask, is it possible that x squared plus y minus 1 squared equals 0? And if it is, when does it happen?
X equals 0, y equals 1.
Okay, so notice if we plug in x equals 0, y equals 1, that's a solution that gives us 0. Is there any other point that we need to worry about?
Y minus x squared needs to be larger or equal to 0.
So there is something in the numerator, that's true, the square root. But is there any other thing I have to worry about in the denominator? Is it just one single point? Just that one, only one point that we have to worry about? Well, it's okay if y is 1, as long as x squared is not 0, right? Because I need to have the total downstairs has to be 0. So is it just a single point? Well, for the denominator, the answer is yes. For the function as a whole, the answer is, well, to be determined. So, okay, we have to avoid that point 0, 1. All right, now, upstairs. Square root of y minus x squared, what has to be true about my stuff inside the square root? Has to be greater than or equal to 0. It's okay if it equals 0, but it's not okay to be less than 0. All right, so here, I need to have y minus x squared should be greater than or equal to 0. And I should have put x squared plus y minus 1 squared just to make it consistent. I should say, look, that should just not be 0. That's what we need. So we can go from the original function to say, we really have two conditions. We've talked about this x squared plus y minus 1 squared, y minus x squared greater than or equal to 0. Another way to say that is that y should be greater than or equal to x squared. Well, we're almost done. In some sense, we found the domain. So the domain is everything, all points, where y is greater than or equal to x squared and is not 0, 1. So that actually describes our domain. But let's draw the picture, because it says sketch. And this is our chance to sort of pull out our inner art history major and just say, how you doing? How you doing? Okay. So, x squared plus y minus 1 squared not equal 0, and y greater than or equal to x squared. Well, let's start with y greater than or equal to x squared. So if I want to sketch this, this is a region. In other words, it's not just a curve. The inequality says I'm going to have a larger thing. Let's just not worry about the inequality. I'll start with y equals x squared. What is that? It's a parabola. So I have y equals x squared. Oh, that's a very not dark parabola. Let's switch to a darker color. Let's see if this is a darker color. It is not. Okay, well, all right, going all in. There we go. Very purpley. Okay. Now, notice I draw a solid line. Why solid? Because I'm including it. I'm including it. If I didn't want to include it, what would I draw? Yeah, dashed or dotted. Okay. Now, the inequality. Y greater than or equal to x squared. See, y equals x squared really cuts my plane into two pieces. So if I pulled out my scissors and cut, I'd have a piece up here, which is, if you like, in the bowl, and then a piece down here, which is out of the bowl. Which one do we include? We should include in the bowl. How could we figure it out if we weren't sure? Plug in, well, a point, not just a number, but plug in a point, right? Well, which point? Well, the answer is any point as long as it's not on the curve. I just need to decide. So, for instance, suppose I picked a point here. X equals 1, y equals 0. Is 0 greater than or equal to 1 squared? No. And that's it. Now I'm done. See, I just have to figure out whether one point is in or out. And once I know whether one point is in or out, then the whole thing is in or out. So I picked a point out of the bowl. I said that's not in there, so the outside of the bowl is not. So the inside of the bowl should be. Finally, I have this point 0, 1. I have to avoid it. Well, how do I do that? I put a little circle here. So an open circle is an indication, look, I don't take that point. But otherwise, I'm grabbing everything else. So we shade it in. So there we go. There is our domain. Okay, ready for the next one? Find and sketch the domain of the following function. Square root of 2x minus x squared divided by log of x minus y squared. Okay. Well, where are some problems? Okay, so one of the first things we see is a square root. I mean, even when you just say it out loud, the function is the square root. Oh, there's a square root. Be on the lookout. Maybe there's a problem with the square root, at least a potential problem. Okay, so square root of 2x minus x squared. Well, that tells me I need 2x minus x squared to be greater than or equal to 0. Now, if I think of the function 2x minus x squared, when is it greater than or equal to 0? Certainly true at x equals 1. It's greater than or equal to 0. It's also true at 2.
When x is less than 2, absolute value of x less than 2?
We've had one suggestion when absolute value of x is less than 2, but what about negative 1? Because that satisfies absolute value of x less than 2. So let's do a quick sketch. So x times, I can think of this 2x minus x squared as x times 2 minus x. And if I were to come and graph it, if I had this curve, y equals x times 2 minus x, where would I hit the x-axis? At 0 and at 2. Now, what kind of curve is 2x minus x squared? It's a parabola, Am I going to open up or down? Down. How do I know? The sine of the x squared is negative. So it's a parabola that's doing this. So when is it greater than or equal to 0? Well, that's the part that's above the axis. So 2x minus x squared being greater than or equal to 0 becomes 0 less than or equal to x less than or equal to 2. So I have to have that x is between 0 and 2. All right. So far, that's the only restriction. What's next? We do see a logarithm. Let's talk our way through the log. So if I see a log, what has to be true about the inside? Has to be positive. So x minus y squared has to be positive, which says x has to be greater than y squared. Now let's think about this. All right, we'll draw ourselves a set of axes here. What does x equal y squared look like? It's a parabola turned sideways. So what you're doing is you're interchanging the roles of x and y. So y equals x squared is a parabola that looks more or less like we normally expect parabolas to look like. X equals y squared is a parabola that would be on its side. So if I sketch it, I'd see something that looks like a parabola that's been turned sideways. Now, you probably have already noticed, drawing with a dotted line, why is it dotted? We don't want to include that because we don't have an equality. All right, which side do we want to be on? Do we want to be on the right hand or the left hand? We're on the right. How do you know? Pick a point. Here's x equals 1, y equals 0. Is 1 greater than 0? Yeah, so that says that the point here would be included, and once one point is in, the whole thing is in. All right. So that's good. Now we already know that x has to be between 0 and 2. So here's x equals 2. And I'm going to draw this as a solid line because I can include 2. I also know I have to have that x is greater than or equal to 0. So that's a solid line, whatever that means. All right. Well, are we done? What's left? Okay. Natural log of 1. Yeah, we don't want to divide by 0. All right. So how do we handle that? Okay. Someone said, look, I don't want to have the denominator be 0. The denominator involves a log. So when does log equal 0? And the answer is log equals 0 when I'm taking log of 1. So I want to make sure x minus y squared is not 1. And that's my way of saying I don't want the denominator to be 0. All right, so x minus y squared is not 1. So that says I can't have x can't be y squared plus 1. All right. Well, what does the curve of y squared plus 1 look like? Offset by which direction do I go? Up, down, left, right. I have a vote for left. I have a vote for up. Anyone want to take down? No one? Anyone want to pick right?
Yeah, I'd say right.
It's to the right. Why? Well,
This is x, it's not y.
well, just think about what happens at y equals 0. What should x be? 1. It's going to go through at that point. In other words, instead of being here, I move it to the right. So you have to sort of think a little bit about how things translate. Ah, man, thinking, that seems uncomfortable. Okay. but it's good to do that. All right, so x is not y squared plus 1, so it's just same parabola, just shifted that direction. So we will try to draw that same parabola, just shifted over, and not, so we're going to draw it dotted. And so, what's our final answer? Well, our final answer is it's the region that's in our bowl, but below 2, except we have this line that runs down the middle that we take out. So that's our sketch. Solid line over here, dotted line, whoops, dotted line here, dotted line there. Now, if we wanted to be a little bit careful, we would say, on these places here where lines cross, you don't include those. So those points are out. Just so, look, if you're in the domain, everything has to work. So if even one part works, throw it out. So you want to be careful. Now you might wonder, have you ever included problems like this on an exam? Because you might be in your exam thinking mode. And the answer is yes. Oh, and they're fun. We get to test how well you can draw things. And it's good times, good times. All right. Well, so that's our domain and range. Let's switch gears and talk about visualization. So when we're talking about visualization, the way we visualize functions is by the use of graphs. And for some functions, you're used to this idea. So for example, for y equals f of x, we're actually very familiar with how to represent a function by a graph, so much so that's often how we think of functions, is we think of them as pictures. And so we get into that habit of a function is a picture, which can be good or bad depending upon what you're doing. Now, how do we visualize? Well, the idea is for every input, here's a value of x, I look at the corresponding output. So here's a value f of x, and I get a single point. Well, that's one point. Now what do I do? Well, to visualize, I look at all the points in my domain. So maybe there's my domain. And I look at the point above each one. And I build up a series of individual dots. And of course, I can plot even more dots. And if I plot enough dots, it looks like it's a nice smooth curve. So in case you're wondering, if you ever see a calculator, I know you've heard about these things before. You got to see them before you took this class. That's how calculators draw, is they say, well, let me just pick a point. Now let me pick a few hundred other points, and now I have the dots. And I'll play connect the dot. Okay, so that's how functions work, is essentially what they're doing. It's a visual representation. For every input, we associate an output up here. Now, how does it work when I have a function of two variables? And the answer is, it's the same basic philosophy. You start and say, well, let's specify our input. So I have some piece, might be everything, but down here, this is my points that I can plug in. So here is my inputs. So this is my domain. And now, what do I do? Well, for every point I can plug in, I say here's a point, x, y. I go up to whatever the height is. So I get this value of z. So the z tells me how far up I go. Now that's one point. What do I do? Well, the answer won't surprise you. We do the same thing for every possible point. So once we do that, we start getting these various shapes coming together. And then all of a sudden, lo and behold, what we see is a surface. So that I can take this downstairs, and for every point I can associate it with the point upstairs. So that's what we talk about when you say visualize a function. is you get some sort of a surface representation. And generally speaking, surfaces aren't flat. Our favorite type of surface is, of course, a flat thing, because we understand flat things very well. And we're going to get to the point where we're going to try to understand things via flat things. All right, so that's when we talk about a graph of a function, that's what we mean. Now, how do you learn to say, what does this look like? Well, one way to do it is to actually go and visualize them. And there's apps you can download that do this. And the other thing is Google is very good at doing this. If you just type in z equals, pick a function of x and y, and do a search for it, it'll pull up a rotating three-dimensional picture of that surface. And you can zoom in, you can zoom out, and it's a good way to get some intuition. Now, unfortunately, it does require a couple of things. You know, it requires a computer and a lot of software. What if we want to understand things a little bit simpler? Well, there's an idea, we call them level curves. And what's going on is the following. We have this three-dimensional thing. So here we go. It's you can sort of see a shadow of it right here. So there's an upside-down bowl that's been stretched a little bit. So I have this upside-down bowl. And what I'm going to do is I'm going to look at what are called the level curves. The level curves say, I want to slice perpendicular to the z-axis. So in other words, I'm fixing a height. So I have several slices. So I have a slice up here, a next slice, so forth and so on, going down. And I'm not going to slice at every level. I'll sort of slice at intermittent levels. And when I do that, I can say, well, where do I hit the surface? So I have my top slice hits the surface at some curve. In this case, a circle. The next slice, again, a circle, all the way down. Well, we call these curves, these are called level curves. They're also called contours. And what they are is they're now curves in the plane. In other words, I forget about the z component completely, and I say, look, these are all in the plane. In fact, what we can do is stack them all together. So I can take all these and just zoom, draw them straight down, and I can get a collection of curves in my plane. Now, the curves in the plane, these are called a contour map. And these various curves here say what's happening at a certain level. All right. So how do we use these? In fact, these have been used in multiple settings. And you've seen things like this before, things like a heat map. Maybe you want to know how hot it is. Well, it will post, there's a map, and it says in this part of the country it's such and such. In that part of the country it's maybe a little bit warmer, maybe a little bit hotter. But what you'll see is there are boundaries. The boundaries are where the temperature is at a certain value. Maybe it's 65. So if you're on one side of the boundary, you're 65 or less. On the other side of the boundary, you're 65 or more. There's one I was looking at yesterday, which was how much snowfall is there in a particular place? And I was looking at it, and like, oh, we're in about the 7.5 inch slice. Yay! But you know, that happens. Topographical maps. Now, if you're not familiar with topographical maps, maybe I can give an example here. Topographical maps are ways to sort of say, what if you want to look at elevations? So we can look at the various elevations. So here's a topographical map here of Kansas. And it's unfortunately not very interesting. So we'll have to change it. But the idea is maybe if you've ever gone hiking and you want to say, well, I want to look at the terrain around me. So what I can do is the topographical map says, let's slice and let's look at things at elevations. And so I can make something up really quickly. So we'll just put in a little bit of a topographical map here. Okay, let's see. What can we do? Okay, let's say that's our topographical map. I don't know. All right. So every line there represents an elevation. Now the question is this useful as is? And no, it's missing something. What am I missing? I'm missing what slices I take these at. So that sort of limits the usefulness. So the other thing that happens is we add labels. So I can put 7, 8, 9. Here I'll put this at 6. And then this will also be 8 and 7, 6. And this will be at 8 again, 7, 6, 5. Just something more or less like that. Now, once you have this topographical map, there are certain things you can start to recognize. So, for instance, what's happening here? I see 7, 8, 9. What's going on? You're going up. So you're going up to a peak. So this is a mountain. On the other hand, 7, 6, 5, what's that? Going down. So, for instance, you might have like an open mine pit that has the elevation stop. And there's other things you can tell. For instance, I didn't do a very good job of this, but you could imagine that maybe I added some extra layers here. And suppose I put these here. And, how do we want these? Should we go up or down? Up. All right. 7, 8, 9. So now it's Twin Peaks. What do you see here? This part. Lots of contour lines really close together, which means what? Very steep. Whereas on the other side, they're a little bit more spaced out, which says, look, if you want to, have a more pleasant day, go up the shallow side. If you're trying to get down as fast as possible, well, that'll do it. But anyways, there's information. There's information. That's the important thing. Now, we're not going to test too much directly on contour maps, but the important thing is we're going to test on these ideas of level curves. So remember what a level curve is. It's where the function is constant. So that all along here, if I pick any level curve I want, it's always the same height. That's the important thing. Always the same height. All right. Well, we've talked about functions of 2 variables, but we can also talk about functions of 3 variables. So for functions of 3 variables, we can still talk about range. We can still talk about domain. There's no good method to draw. And the reason there's no good method to draw is we have 3 inputs and a 4th output. So somehow we have to draw 4 directions on a piece of paper. It's already tough enough to draw 3 directions on a piece of paper. 4 is just right out. We're not even going to try it. So we're not going to look at pictures, but we can still look at cross sections. So here, instead of talking about level curves, so a level curve is where the output is the same. I'm fixing the output and saying, what do I get? We can talk about now level surfaces. So level surfaces are I fix the output and see what I get. So here is a function. h of x, y, z is z minus x squared minus y squared. What do my level surfaces look like? What are they? Because it says that we should find and sketch them. Well, if I want a level surface, that says I'm going to fix the output. So here's my output. I'm going to set it equal to something. Just some number k. K is z minus x squared minus y squared. So that's what a typical level surface looks like. For some choice of k, then I'll get some surface. Now it's written in a particular way so that we can actually do something with this surface. So this is z equals x squared plus y squared plus k. Now, how could we find what this looks like? So for instance, what does x squared plus y squared look like? It looks like a circle if that was in the plane, x squared plus y squared. If I say z equals x squared plus y squared, what do I see? I would say now is the time for review, but because of our Canadian friends up north, we missed out on the day of quadric surfaces. So it's good to know what this one looks like. So if you think about x squared plus y squared, just temporarily just that, if I said, look, for a second, ignore x. So I'm in the yz plane. I'd see z equals y squared, which means I would see a parabola. And then I say, okay, now let's forget about y. So I'm in the xz plane. Z equals x squared. What do I see now? I also see a parabola. We're going to the xz plane. And now I put these together and say, oh, it's a bowl. So that's what x squared plus y squared is. It's a bowl. All right. So I have this bowl, z equals x squared plus y squared. So if I set k equals 0, then that's just the straightforward bowl. So here's k equals 0, which is z equals x squared plus y squared. What if I set k equal 1? It'd be the same bowl, but shifted up by 1. What if I set k equal 2? Again, same bowl, moved up by 2. So what I get is that the level surfaces are bowls. And this is one example. There are many possible, but that's it for time. So we'll pick up again next time.